Right. So again, great to see everybody. We are going to pop up the agenda really quickly here. Once again, just to give you a little run through of where we will be as far as the day as a refresher. Again, today, both myself and my co-coordinator, Brian Abramowitz, are here, along with our fearless leader, Dr. Bruce McFadden, Jeanette Perlow, and Frost Science Director of Communication, Dr. Kate Parker. And we have a very special guest today with us, Dr. Julie Boker, which you'll meet in just a few moments. Throughout the day, feel free to unmute, ask questions, or type in the chat box, which may be easier for us to monitor as a group. We're happy to take those questions as they come. And again, if you need to run to a bathroom or anything like that to get a cup of coffee refresher, please do that so that we can continue on and you're comfortable. So I'm gonna pass things over to Brian really quickly to talk about learning goals.
Thanks, Stephanie. And we saw in your applications that each of you had your own individual goals of things that you wanted to achieve today. So these are just things that Stephanie and I brainstormed of as the team was developing this workshop, things that we hope to achieve. And just starting from the beginning, each of the teachers here today, by the time this workshop is over, you'll have a better understanding of the content that is being developed here. You'll be able to go back to your classroom with a new sense of self-efficacy, the idea of you'll be able to do this with more confidence and teach this in a way that you could be really proud of and comfortable doing so. We also are going to introduce you to the new exhibit taking place at the Frost Museum. And although today is virtual, really hope one day you'll make it out there and get a chance to see it for yourself. We're also going to talk to you about our program, the Scientist in Every Florida School program, what we offer and how you can get involved. And finally, you will have the opportunity to execute the program, the SEFS program, but also the workshop, the lesson that you are going to be participating in today. And then ultimately submit a reflection about the experience, implementing it in your classroom to share with the group after today's workshop. So as I said, we represent the Scientist in Every Florida School program, or SEFS as we like to call it. And you can see there are a few main components or aspects of our program that we primarily focus on. One of those is this idea of a scientist visit. Typically, a teacher will request a scientist visit through a Google form. They'll tell us school name, grade, what topic you'd like us to cover, when you'd like it to take place. All this information will come directly to me and Stephanie. And at that point, we'll start reaching out to scientists. We ask that you provide us at least a 2-week window for that visit. And at that point, like I said, we'll start reaching out to people once we find someone that is available that day. They're typically all excited to do it. So it's just an issue of availability, whether they're in the field, in their lab, or available to participate in this visit. Then we'll connect them with you as the teacher, scientist, start to have that conversation of here's my vision for this visit. And once those visions are aligned, the date is set, that visit will take place. And it could be a role model visit. It could be something along the lines of, I was the first one of my family to go to college. Here's how I had to overcome some challenges and do so. It could be a content specific visit. I mean, Stephanie and I are former teachers. We know that there is so much content to cover. So everybody has their little bit of content area weakness. So it could just be, you want to bring in an expert to talk about something you don't feel as confident about. So there are a lot of different, almost endless number of opportunities to bring scientists into your classroom. And you could just reach out to us through the Google form on our website and request one for yourself. The other opportunities that we provide is professional development opportunities. We provide at least usually 3 to 4 of them per year. We have a big one in July where we bring in about 30 to 40 teachers to Gainesville when pandemics permit. And we put them up in hotel, provide food. And throughout that week, we have about 3 to 4 teachers that are paired with a scientist. They collaborate throughout the week. Teacher brings their pedagogy and curriculum expertise. Scientist brings their content expertise, and they co-develop a lesson that will be taught in the teacher's classroom at some point throughout that year, as well as other ones like the one you're experiencing today. We also have another paleontology one coming up. In the summer, we have a plant pathology one coming up. So I encourage you to subscribe to our newsletter or visit our website often, or our Facebook group to be some of the first that hear about those opportunities so you could get your application as soon as you can. And lastly, live stream programming. We have about 30 to 40 live streams that take place per year. Partnerships with the Anjari Foundation in Palm Beach, in Mounts Botanical Garden, on botany themes. So there is a variety of these that take place throughout the school day and focus on a standard aligned topic to reach a great deal of teachers. And after each of those, they are posted on our YouTube channel.
All right. So before we jump into our first speaker, we wanted to let you know that you can find today's agenda along with a lot of the important documents that you'll be seeing throughout the day in a Google folder link that we're going to place in the chat box right now. Actually, I'm going to post that in the chat box along with the PowerPoint that you're looking at, because there's hyperlinks in that document as well. So you should have that there now in the chat box, and be sure to add this folder to your Google Drives just so it's around for easy access. Inside, you're going to find today's PowerPoint presentations. Once again, you'll find a lot of links that Brian just mentioned, such as the SEFS Spotlight newsletter and our events calendar where the live stream events are located. So check that out for sure. In fact, I'm going to click on that live stream calendar for just a second, just to kind of show you the rundown and how this works. And in particular, because there is an event that I believe, and I know Brian believes, will be a great mesh or match with what you're doing here today. We have, in conjunction with the Florida Museum of Natural History, with where we are housed, a wonderful Florida Fossils 360 tour that will be hosted by ourselves and the museum. And our speaker is Dr. Bruce McFadden, whom you will know. So we encourage you to come to this event. You can register for that Zoom with your classes. There's extension activity guides included, et cetera. So great place to find, again, some of that information that Brian referenced. But this little Google folder here will have a bunch of important information for you moving forward. So definitely have that, again, kind of bookmarked or linked to your own Google Drive. So at this time, I'd like to introduce Dr. Julie Beaufort, who played a pivotal role in the creation of field testing, evaluating, and really building and creating the lessons that we're going to be looking at the top of the morning here. You'll get to meet her. She's going to be telling you a little bit about chewing on change. She is the Director of Grants and Acquisitions and Special Programs and Project Development now with the Alachua County Schools. Prior to that, she worked for CPET at the University of Florida and was heavily involved in professional development for teachers around the state. So at this time, I'm going to stop share so that Julie can share her screen.
All right. Share screen. All right. Well, thank you for that introduction. You know, it's kind of weird. I just started in January, so that's the first time I've been formally introduced with my new position. So that's kind of interesting. So how's that? Can we all see? All right. Well, thank you everybody for getting up early on this Saturday morning. I know that it's very, very appealing to just stay in bed, especially when we have this chilly weather. So thank you all for what you do every day for our students. And to the SEFS team, I'm so happy to be a part of it. Yeah, so Dr. McFadden had asked me to talk a little bit about this curriculum, which is quite possibly one of my favorite things that I've had the opportunity to work on. And during my time at CPET, this was just a phenomenal collaboration, and I'm delighted to see it still moving forward. So I think that you guys are going to really enjoy this. So just a little bit about this particular development. As Stephanie already had on the introductory screen, this was a collaboration. So we had two classroom teachers, Jennifer and Jessica. They were both high school teachers. Jennifer teaching more at the time, general level, on-level biology, Jessica teaching AP biology. And they spent some time with Dr. McFadden here in the collections, and he brought out a bag of teeth to them and said, what can you develop with this? So they spent time brainstorming and going back and forth with Dr. McFadden to develop the lessons that you are going to be looking at today. And one of the things that Dr. McFadden specifically challenged them with was the idea of horse evolution being a phylogenetic branching pattern as opposed to a linear pattern, which is unfortunately often depicted in textbooks, in museums. So really trying to help students understand the evolutionary process. And then I was kind of the middle person between, working between the teachers and Dr. McFadden. And then we were fortunate to have graduate student Sean Moran working with us as well. And then I'm also going to show you some of the research that a postdoc, Dr. Cheryl McLaughlin, also did part of this project. So these are fossil horse teeth, and they are precious and very special, and they stay in the collection. So what we wanted to do was get these out into the classroom and allow students to be able to enjoy this as well. So Jessica and Jennifer developed this sequence that you guys are going to go through today. And it's phenomenal. The very first time this was rolled out, was the August, I think it was the August, right after the teachers had been here. So Sean had actually been out in the field, came back, and he and Cheryl McLaughlin essentially jumped on a plane, flew up to Ohio to watch the very first implementation of this lesson or this curriculum. So what Cheryl was looking at, she was a postdoc, and science education was her particular area from her dissertation, was looking at this curriculum. Does it encourage inquiry? Does it really tap into those higher elements of Bloom's taxonomy? So we're really trying to get at that, not just a regurgitation, not just, stand and preach from the teacher, but really engaging the students. And as you can see from Cheryl's observations while she was there, and this took place over a week, that it really does hit on those higher levels. So the students were really needing to apply their understanding. They needed to analyze the data. They needed to then create, and that especially comes into the third lesson, the last lesson, where they really need to synthesize all of these pieces to make sense of what's going on with the evolution of the horse. And with that very first implementation too, we also used an assessment. So we had a content measure that was developed. And this was actually wonderfully co-developed between the teachers, Sean and Dr. McFadden. So it's scientifically sound, which is something that's very important to me coming out of our world. And as you can see, the students definitely increased their knowledge of evolutionary concepts. So this was wonderful. This was encouraging, but still pretty a small sample size. So we've got proof of concept in one classroom. And of course, Dr. McFadden, he wants to go bigger. He wants to do it up. So what we did next was, went into a field testing situation. So we presented at an NABT conference, National Association of Biology Teacher Conference, and recruited from there. These educators did not get paid. They received no compensation other than all the materials. So at this point, the 3D printed horse teeth, we sent them calipers, we sent them horse cards to actually implement this curriculum. And the response, I was just overwhelmed at the response. I would say I was not prepared for this much interest going out the gate. But as you can see, we did end up with 26 teachers in 16 schools. We had a very large turnout in Michigan. One of our teachers actually got her entire district to implement this, which was absolutely wonderful. But we covered pretty much the entire country in this implementation of the field testing. At this point, what we were looking at is not just their content knowledge. So we wanted to, of course, say, did the students learn? Did they increase their content knowledge? But more importantly, from an evolutionary perspective, from an evolutionary education perspective, did they increase their acceptance? And that acceptance of evolution is a really hard nut to crack. So we used the MATE, which is the measure of acceptance of the theory of evolution. We also asked for teachers to give us feedback on all of the lessons, to document how the implementation went. And perhaps even more importantly, we asked for student feedback, because often we leave our students out of this whole formula and we don't ask for theirs, but we got it. And as you all know, students can be completely honest and blunt. So that was great. So what we found was that indeed content knowledge did increase, and we had statistical significance in that increase. So our content knowledge instrument that we developed, the top score was actually 25 points. So as you can see, our mean still is maybe a little bit lower than what we would like, but at the same time, we have very complex questions on there as well. It's all true, false, and multiple choice with a couple of explain questions. But overall, we were pleased with that. Okay, so the students learned. But most exciting, especially for me, was that we had statistical significance in the students' acceptance of evolution. So utilizing this 3-lesson curricular unit helped the students come to terms with evolution and accept that indeed evolutionary theory is real. It is based on fact. So that was absolutely phenomenal. Some of the feedback, just quickly, we had very positive feedback from both the students and the teachers, which was encouraging, and you can read that on your own. But there were some challenges, and these are challenges that, of course, every time through with something new, we tend to kind of underestimate our time that we need. So that was one of the first challenges, is that we had originally hoped that we could fit this into 5 days with 45-minute periods. But the reality is the implementation, if we did it with fidelity, took a little bit longer. And of course, it depends on the class and the level of the students and their prior understanding. The other thing with the teachers and the students was creating phylogenetic trees. So the teachers struggled a little bit with helping the students understand creating phylogenetic trees. And the students were particularly challenged with, there's no one right answer. That really, really bothered the students, that what they were working with, they were making a hypothesis using the data that they had available, but that there isn't one definitive answer. And that is really disconcerting for students, especially our students today. They want to know. And then also for the students, which was interesting, and we wouldn't have known if we hadn't asked for their feedback, was the discourse surrounding evolution and creationism. So we saw this surface in different classrooms. In some classrooms, the teachers seemed to allow more of this discourse, and in others, they did not. So that is kind of a default to the professionalism that you all have in your classroom with how you approach that. But those students that were very much on the side of creationism seemed to really kind of struggle, of course. And then those that were on the other end, very soundly accepting evolutionary theory, were a little bit frustrated with some of their classmates. So that was out there. And I think actually I'm going to skip this because you guys are probably going to talk about it. And this, I don't know if y'all are going to show this, but this is absolutely one of my most favorite images. So this was put together by Sean Moran. And what you can see here in this little snapshot are all these beautiful teeth. So I'm sure that they will talk about Sean's mission of scanning all of these teeth. And then he created this absolutely beautiful poster that I think should be a poster on the wall, but absolutely beautiful. But this is what you guys are going to work with. And what you can't really tell on here is the scale. So this very first ancestral horse, teeny, so teeny. And then we get to modern and it's quite large. So it's really striking. And the conversations that the students have, the conversations that teachers have when we've implemented this. I've used it with pre-service elementary teachers. It's really so fun to hear that dialogue. So I will end there so that you can actually get into it. And Stephanie's already provided you with all these links, but if I can be of a resource, if you have any other questions that I could answer from the research side or implementation tips, please don't hesitate to reach out to me. And so I will stop sharing. And I hope I didn't go too far over my time.
No, you did great, Julie. Thank you so much. That was very insightful. It's great to see kind of, again, the insight and the history into making Chewing on Change. I know we're really excited. It's an amazing lesson. As a former middle school teacher in Palm Beach County, I can say from experience in teaching the lesson that my students really loved doing it. They comprehended complex and often challenging topics and concepts with ease, as a result of experiencing the different lessons. And yes, the teachers are going to get a little taste of that today, but it's so nice to have the full curriculum guide with all of the teacher keys and the different quizzes and aspects that you put into this, you and the rest of the team. So thank you very, very much.
You're welcome.
Hurry up in the beginning so you had a little more time to tell everything you need to tell. So thank you for that once again.
Thank you. All right, you guys have fun and holler if you need anything.
Sounds good. Brian, can you give me share privileges again? Because I think I've lost that.
Sure, go right ahead.
Wonderful. Awesome. There we go. Okay, so now onwards and upwards here. Here we go. Let me see. I have just got to find my place on where I am. This is our next speaker, Dr. Bruce McFadden, and he is the director of the Thompson Earth Systems Institute and therefore the scientist in every Florida school program. And those of you that were on the call the other evening heard that he is in fact a fossil horse expert. So we're going to hear it, as he said, straight from the horse's mouth. Bruce, I'm going to let you take it from here.
Okay, thanks, Stephanie. Can you hear me okay?
You sure can.
Good, thanks. Before we advance the slides, I just want to say that was a really great introduction by Dr. Bokor, and thanks to her for all of her hard work in terms of learning research, but also implementation on a national scale. Really appreciate that. So yeah, so ever since I was a graduate student a long time ago during the Pleistocene, the ice ages, I've been interested in fossil horses because of a mentor I had in graduate school. So I guess what I'm known for would be using fossil horses as evidence of evolution. And one of the horses that I'm particularly, can you see my cursor as I move it, Stephanie? No. Okay, that'll be okay. So in the skeleton on the left is a skeleton of an 18-million-year-old horse found from a fossil locality in Florida called Thomas Farm. And tooth number 4 in your study set represents this Florida horse from 18 million years ago. And then if you're interested, my book, Fossil Horses, which was published in 1992, is the 4 millionth most popular book on Amazon. So you'll need to rush and get to it because it's a rapidly depleted stock. I'm just kidding. So yeah, with that introduction, if you would please advance the slides for me. And I'm going to turn on my my stopwatch so I don't go too far over. Good. Okay, so for those of us who teach about the theory of evolution, there are about 10 different kinds of or lines of evidence, all the way from DNA to the color of moths in England, the next one there, to what's called homology, how different bones in vertebrate limbs are of similar origin to Drosophila genetics, to the construction of family trees or phylogenies, to the classic example lower left of Darwin's finches on the Galapagos, to the origin, to laboratory experiments in chemistry at the University of Chicago about making the origins of life, to to the developmental pathways or embryology of life, as depicted on this T-shirt, to some of the critical fossils like Archaeopteryx, for a long time was considered to be the first bird from about 150 million years ago in Bavaria, Germany, to, last but not least, the evolution of the fossil horse in all of its glory over the past 55 million years is widely touted as one of the textbook or museum classic examples of evolution as depicted from the fossil record. So you're getting in this lesson sort of one of the classic examples that the discipline uses to promote an understanding of the pattern of evolution in geologic time. Next, please, Stephanie. Yeah, so this project was not something that I started. I was asked by Julie to lay out some fossils and talk to about a dozen or 15 teachers back in 2014 when they came back to school for a campus summer professional development on genetics and evolution. So I laid out the study set of fossil horse teeth in the left. Stephanie, if you would bring your cursor over there. And by the way, what you should know is many of those teeth in those boxes on the right side, are exactly the same teeth that are 3D printed in your lesson, in your study set. So that's what they look like as real fossils. Of course, they're white because of the plastic that prints out in 3D prints. And this lesson plan the lesson plan number 1 would not have occurred without the creative vision of 2 of the teachers who developed it. And this is Jessica, who taught at Orlando on the left, and Jennifer, who teaches at a public school outside of Cincinnati now on the right. And they're the ones who I basically said, here are the teeth on the left. You now have an hour and a half or so. Go away and work in groups and come back with a lesson plan. I had no clue what they were going to come back with. What they came back with was lesson plan 1, and it blew me away. Far better than I could have come up with. So this was co-created by a team of teachers during a professional development 8 years ago on the University of Florida campus, and it's been since implemented the way Julie mentioned and in other sites around the country. Okay, Stephanie, next, please. So we're going to primarily, we can't do all 3 lesson plans today. There are extensions, and in fact, I have another one using big data and computer science that I'd like to develop new with a group of teachers. If you might be interested in working on that with me in the future, that's another thing. But basically, we only have time to do the first of the lesson plans, the one that they developed during that PD, and it's called it's called Chewing on Change, and your workbook is in the Google Doc, and the materials that you need in order to do it were sent to you along with the caliper for you to basically measure today the teeth and see how they change through 50 million years. So this is exploring the geologic timescale via changes in fossilized horse teeth. And these are all changes that were in response to climate change and the evolution of the diets, the plant foods that these horses ate through the course of the 50 or so million years of their existence in North America. Next slide, please. Yeah, so we want to go through some vignettes, and these are the same illustrations that you have in your workbook. What did the world look like when horses first evolved, when first originated? And that's about 55 million years ago, during the beginnings of the Eocene. And so if you look at places like in England or out in Wyoming, during the Eocene age rocks at about 55 million years ago, the world was very much what we might call a hothouse or a greenhouse environment, and it was much more tropical than it is today. And the origins of fossil horses occurred in this greenhouse or hothouse environment, and they were smaller. And the tooth number 1 in your set is of Spherhippus, which is also called Eohippus in the older literature or some other terms. And this tooth, the first upper molar, is where we start the evidence for fossil horse evolution in your measurement journey today when you break out into your groups and you construct the graph. So that's what horses originated in the tropical environments. There were no horses in Florida yet because Florida as a peninsula didn't exist yet. Florida at that time was underwater, but in other places like Wyoming and England and France, there were tropical sediments that preserved the early ancestors of the modern horses. Next, please. Then if we segue on to about 35 million years ago, a place where we're working now in Nebraska to collect fossil horses, we see that the horses, again, not yet in Florida, but if we go out to Nebraska and some other places out west, we see a horse called Mesohippus, which is number 2 in your study set. And just a second, my screen changed. Okay, and what we know is that these horses were there were no grasses. Modern day horses prefer to feed on grasses in prairies. But 35 million years ago, there were no grasses, or the grasses were exceedingly rare. So the horses that evolved about 35 million years ago, when there was a major change in climate, had teeth that were adapted to feeding on soft or leafy vegetation. They're what's called browsers. Next, please. When we get to the Miocene, from about 23 to 5 million, or about 5 million years ago, we're finding lots of horses in hundreds of localities throughout the fossiliferous sequence in Florida. Florida is a hotbed for understanding fossils and paleontology because fossils are preserved almost everywhere around the state. Our collection has more than 1,000 fossil localities that are used to provide the evidence, not just for horse evolution, but also for other kinds of animals that lived during the Miocene when the peninsula really first got going. So we find during this time also, by about 10 million years ago, grasses had evolved, not just in Nebraska and the prairie grasses of today, but throughout North America. And we know, based on the change in the shape or adaptations of Miocene horses, of which they're represented teeth numbers 3 through 12 in your study set, these horses had a variety of different kinds of morphologies or shapes of their teeth, and they were feeding on different kinds of vegetation. Some were still feeding on the soft leafy vegetation like the more primitive horses, but other horses were more advanced, and their tooth adaptations indicate that they were feeding on grasses, and they became grazers. Next, please. During the Pliocene, we get a further elaboration of grazing habits, the grasslands, during this time from about 5 to 2 million years ago, and different kinds of horses were feeding on grasses. There were small horses like tooth number 13, and there's a larger horse, very similar to the modern horse. It actually is an extinct species of Equus, number 14. And we know that these animals were feeding on a regime primarily of grasslands that existed throughout much of North America. As the forest gave way during the Miocene, the Pliocene was a time of drying, of rapid sea level changes, and of the expansion of grasslands during this time. And the horses adapted their teeth through the course of genetic mutations and evolution, random mutations in evolution. They adapted to feeding on these kinds of grasses. Next. During the last epoch of the time of horses, which scientists call, which are the Ice Age, but scientists call the Pleistocene epoch, which goes from about 2 or 2.5 million years ago till 10,000 years ago. This was a time when the world was heavily glaciated. This was the time of mammoths and mastodons. The mammoth that you will see in your video journey with Kate later this morning lived in a regime during the Pleistocene like this. But in addition to the mammoths and mastodons and the snow-capped areas in the northern reaches of the world, the north of the hemisphere, for example, in Florida, there were no ices. There was no ice sheet. but the climate was dramatically changed. It was cooler and drier, and horses like Equus in the skeleton that you see on the right in this image, which we have on display in our exhibit, were also adapted to feeding on grasses that evolved in temperate, drier habitats or climes. Next, please. Yeah, so our lab materials are organized. We had an initial set of 15 teeth, but to sort of we decided that there were about a dozen that were really important to tell you the story today. So you have in your study sets all 12 of the 15 teeth. You do not have numbers 5, 6, and 10, and that's okay because that was deliberate in the study set. We wanted to abbreviate the exercise. You have the worksheets, you have the 3D printed fossil teeth, you have calipers. You should have at least one box of colored pencils. You should use your phone or calculator if you want, a straight edge and a writing utensil, which will help you in determining the evolution through time of horse teeth in your study set. So, Stephanie, do you want to mention a little, are you going to talk about the organization or should I just talk about it?
You can go ahead if you'd like, that's fine.
Yeah, so the first thing I would do is when you do the breakout groups, organize your teeth numerically from number 1, which is so tiny that we put it in a little bag because you almost would miss it, to number 4. Number 14 is actually the one from the Pliocene, but you'll have number 15 as well. Organize the teeth separate from 1 to 15, but you won't have 5, 6, and 10, as I said, because you only had 12 of them. And organize them so that you see the face with a number on it, because sometimes teachers and students are confused about which side of the tooth am I supposed to measure? Am I supposed to measure this side? Or am I supposed to measure which side of the tooth I'm supposed to measure? So I have developed a convention for you in your study set that the side of the tooth where you're going to measure this long ridge is always indicated by the number of the specimen. So all the numbers are on the side that you're going to have to measure. It makes it easier for you. Okay, I think we can move on, Stephanie.
Very good. Did you want me to start the lab directions or would you like to continue on that?
You can do that. Where's the picture with the teachers measuring with the calipers? Is that in your set or my set?
It is. You want me to forward to that real quick?
No, you. Why don't you take it over from here? Because what I wanted Stephanie to do, mine was an introduction about the overall content within which, or the environment within which fossil horses have evolved over the past 50 to 55 million years ago. And the times, okay, that's a good point, Stephanie. The age of the horses go from 55 in the top to about 10,000 years in the bottom. And this is what we've gone through. And each of the pictures that I've shown you in previous slides are the same pictures that demonstrate the environment in your lab book, as well as the teeth that go along. So I wanted to give you some context and some scaffolding for the overall thing that you want to do. But now, and also thanks to Julie, because Julie also helped to bring the scaffolding along as well, plus also the significance of what the teachers are teaching and the students are learning about the content, but also the acceptance of evolution, which is a very important nut to crack, as Julie said. So Stephanie, why don't you take it from here and talk about the nitty-gritty details of the implementation, and then we'll break out into study groups, correct?
Yes, that sounds great. Thank
Okay,
you.
you're welcome. Thank you.
Stephanie, before you do so, I see that Lydia has a question.
Sure.
Yeah, I just had Mr. McFadden kind of really tiny when you were showing the teeth of how to measure them, because I was kind of fiddling with it yesterday to see, and I didn't quite understand. Oh, you are? Okay.
Yes.
Yeah, so there's some finesse required in the use of the calipers, etc. And we understand that some students don't know how to use calipers, so there's a learning curve there. So all this, the tools of the science, I actually also, if you have magnifying glasses handy, we didn't put this in the study set, but in order to look at this small tooth, with my sight, I really do need a magnifying glass. So if some of your students wanted to take a closer look at Spherhippus, the 55 million year old horse, it might behoove you, if you had some magnifying glasses in your school, that would help as well. Okay, so I'm gonna thank you for your attention. I'm gonna be here for the entire lesson, the entire morning. I'm gonna go into breakout sessions. So if you have any questions for me during the breakout sessions, I'll be going from one room to the next, as well as the entire team, to make sure that you have enough background and encouragement to know how to proceed. So Stephanie, if you would continue, please.
Sure, absolutely. Brian, I think there might be a couple more hands raised, or were those the same ones? I'm
I
somewhat.
see Jeanette has her hand up as well.
Jeanette, go
I
ahead.
I just want clarification on the pronunciation. Is it Spherhippus or how do you?
Spherhippus or Eohippus is the other name. Spherhippus is a particular type of early horse that's only known in Wyoming.
So is the F silent?
Spherhippus.
Okay.
That's the
I
way
hear the F now. Sorry.
that's the way I pronounce it. But if you read in other literature, that's a name. This has to do with the scientific nomenclature of extinct species. It's getting into the weeds, so to speak. But Spherhippus is a type of tiny early horse that's primarily found in Wyoming.
Okay.
Okay, and that's where the tooth comes from.
Right.
All right. Thanks for that. Thanks, Jeanette.
And I think one other interesting point to bring up on that, if you look at the front of the curriculum guide in the folder, I believe there's two horses on that image. One is very, very tiny, and there's a larger modern horse looking down at that. That's that Spherhippus horse right there that you're looking at, that little tiny guy that looks about the size of a Chihuahua. So imagine, right?
Yeah.
I think just a couple more things before I move off of this slide. Bruce mentioned, and thank you for that, Bruce, not only where the numeric numbers are on the tooth, that's the side you're going to measure for one of your measurements you'll take, but also to place your teeth in order from 1 down to 15, well 12 teeth on your table there in front of you as you work. And the other thing I would do, just so that there's not confusion for yourselves as you are working in your groups, is mark off 5, 6, and 10 on your sheet. And you see here, I went ahead and numbered 1 through 15 along the side of the catalog numbers. And I think it's kind of neat that you're seeing the actual research grade information on this sheet. You've got not only the age in millions of years, but you've got the locality of where that tooth was found or discovered, its species, genus and species there. And then you've got the UF catalog number. So these are true teeth, as Bruce and Julie mentioned, in the collections at the University of Florida and the National Museum of Natural History. So that's pretty cool. So let's see here, moving on to the next slide.
Latoya, you want to ask your question?
Go ahead.
Good morning. Really quickly, is it possible you can show me exactly where that form is located in the Google folder, or will we do that later?
I'm going to I'll go ahead and stick it in the chat box now just to make things easy for
Okay.
you.
Thank you.
I will go through again where to find it. The Google folder link and the PowerPoint link that I'm working off of in PDF form is right there in the chat. So that first link will open up the folder and you'll see lesson resources inside that folder, and that's where you'll find the lab itself.
Thank you.
You're absolutely welcome. No problem. So let me just scroll back down here to this slide so I can see where we are, and I will explain what it is you need to do. Okay. Alrighty, here we go. So we're going to get you prepared for this lesson, and the first thing that I want you to take a look at before you go into your breakout rooms, we're going to kind of walk through the different things that you all will be doing. And I'm going to grab my copy so I have it here in front of me as well. On that very first page, which is page 23, Bruce referenced those images, and I'm going to have those in the chat box for you. There's a slide deck. Let me get my chat box going again here. There's a slide deck that I've just placed in the chat box of those images for your reference. And it's probably a good idea to open that link and have that tab kind of ready when you go into your breakout so you can use it for reference. What you'll do on the first sheet where it says pre-lab, you've got that list of paintings of each epoch, and you're going to be jotting down bullet point style some observations that you make. So again, we're making you be the student here, but we're kind of giving you a little insider information on the backside as far as what it is your students should be kind of learning throughout the process as they work through this lesson. In this particular part here, it's important that you tell your students, in addition to faunal observations, you should definitely be making some flora observations specific to the vegetation of the area at that time. Is it forested? Is it a mix of maybe forest and grasslands? Or are you looking at a grasslands or savanna dominated scene with really no trees? And that's going to be important as they start to make these connections. So on that first page, this is basically a 5-minute exercise of jotting down those bullets. And again, you've got that link to the epoch images in your chat box. If you flip over to the back side of the page there, you're going to see each of those epochs, and there's a square box. And on this section, the student is to sketch a tooth that's representative of that time period. And on that table that we've already been referencing, that very first column of epoch, you can use that same slide deck of images to figure out if it's 55 million years, for example, it's Eocene, right? So you'd have the students write the epoch, and they're going to find one tooth, just one, they don't have to pick more than that. Some of the epochs have multiple teeth represented in them. And that's really to show that it's not a linear evolution with horses. Rather, there are multiple species sometimes of horses living at the same time. So you'll have them pick one, you'll sketch one tooth real quickly of each of these epochs on this page. And again, about 5 minutes here, just to kind of keep track of your time with your group. If you roll over to page 25, and this is where we're going to get into a little bit more of the measurements, that is a reference guide to the tooth measurements that you're going to be taking. There'll be 2 tooth measurements that you take, and then those 2 measurements will help you make the calculation for the final column, which is the Hypsodony Index HI. And I'll get into that in just a second. And Bruce may want to expound upon that as well. But on this reference guide page, you see this little image right here. And these are the 2 measurements that you will be taking with the calipers. The first measurement, A, is called the crown height measurement. And that is going to be taken on the numbered side of the tooth, as Bruce mentioned. The tooth has this, on most of the teeth, there's this pronounced, what we call a mesostyle here. This mesostyle is that ridge that sits along the tooth. Some of the smaller teeth, you kind of can't see that as well. It's there, but it's very difficult to see. On that side of the tooth, just as you see in this image, you'll use the calipers, and you can see an example here. So you use the caliper as such, and then you read the measurement in millimeters. And that's what you're going to put for the crown height onto your table under a crown height in millimeters, which is that third to last column on the table. For the second measurement, measurement B, you're taking the APL measurement, and that stands for anterior, posterior, lateral. And that measurement, you'll notice the mesostyle sits at the top. So that little bumpy ridge is at the top when you hold your calipers. And you'll again take that measurement in millimeters, and you'll put it in the APL millimeters column, which is the second from the right there, that last column, second to last column on the right. And then those 2 measurements you'll use to calculate Hypsodony Index. And this is kind of interesting. So Hypsodonty, we call it HI for short, and it's basically a ratio of crown height to APL. So crown height divided by APL gives you HI. And what's significant with that is Bruce mentioned browsers and grazers as we were going through the pictures. And you'll see this change in environment happen over time. If the Hypsodony Index is a number that is less than 1, that is an indicator of browsing. And if the Hypsodony Index is greater than 1, it indicates that that animal, that species is a grazer. So you're able to discern the diet of these organisms based off of the teeth Hypsodony Index. And so again, browsers is greater than 1. Browsers is less than 1. Grazers is greater than 1. Okay, I hope I didn't confuse anybody just now. Browsers is less than 1. Grazers is greater than 1. And again, if an animal is a browser, they tend to eat more leafy materials like from trees, and a grazer tends to eat more grassy material. And that again is also significant because grasses tend to have minerals incorporated in them called phytoliths, which are basically silica, glass-like abrasive material. And those particles, as the horse is masticating or chewing, it grinds and wears away the teeth. And I often ask my students in class, why would that be bad? What would that do? And you'll get a lot of great discussion out of them with regard to that. So thank you, Jeanette, for putting that in that chat box for me. So are there any questions?
Did I get that backwards or is that right?
No, you did that right.
Okay.
Eating grass is greater than 1 and a browser is less than 1. That's correct. Are there any questions at this point as far as the measurements? You're taking a crown height measurement, which is A, an APL measurement, which is B, and then you're going to divide crown height over APL to get HI, which is that final column. And HI stands for hip stati. And you're going to look at those teeth that you sketched, and you're going to look at those scenes that you've kind of made observations from, and you'll actually see how adaptation and change happens in the species over time. Any questions? I can't really see the chat, so.
I would say, can you hear me okay, Stephanie?
I sure can.
Yeah, a comment about the use of the calipers. The student, you should let the students know that they can round off their measurement to the nearest millimeter. They don't have to fret about whether a tooth crown height is 61.123 or 125 millimeters. If they could round it off to either 61 or 60, depending upon where the scale lies between two values. The point I'm trying to make is that the measurement should be only like 61 millimeters or 5 millimeters or 72 millimeters. You don't have to worry about the decimals. The picture will emerge with that on its own.
Great point. And another point that you just made me think of, Bruce, is that in the full curriculum packet, there's teacher guides and teacher keys. So you'll get in there's a key that shows you basically the measurements for these teeth over time too. And you can use that for your own purpose when you're teaching and executing a lesson like this in class. So thank you for that, Bruce.
Another thing that the teachers need to know is that there's usually at the bottom of the tooth, there's a mesh. Can you see that right there, the mesh on this equus tooth?
Can you turn it sideways so we can see the difference in texture?
Yeah, so that's the crown. Okay, so orienting on that picture above, that's the crown height. Okay, what I want you to all understand is that these are 3D printed teeth, and each of the bottom of the teeth has a mesh, and that has nothing to do with the tooth. That's how that was printed on the glass plate that extrudes the plastic. So if the students say, what is that mesh at the bottom? That's not really part of the tooth. And you need to understand that then the students can understand that's part of the 3D printing process. And most of the teeth have this mesh at the bottom. Some I've pinched off, others it's more complicated, but actually this tooth now can actually stand up on its own, almost stand up on its own, because that's the way it was printed out. Okay, thanks.
So when
Sure.
when we measure, then we don't account for them. You said we measure on the side of the number. And
Yeah, you measure on the side of the number and you measure the long ridge, and don't worry about the mesh.
oh, the
We
ridge.
use the same part of the caliper?
Yeah, just the way you're doing, Lydia, just the way you're doing it.
Like
Yeah,
that
I
would-
see that there is a second part on the top used for measuring as well. We're gonna use that one as well?
You're going to use that. That's the second measurement in.
Okay, so that's the APL.
You're doing both.
Okay.
Can you, if you put me in presenter mode, excuse me, your view, you'll be able to, there you go. Not presenter, but
Spotlight or.
spotlight, you can see what Lydia was doing is correct. This is the first measurement along the mesostyle. That's the crown height measurement A. Measurement B that's the grinding surface of the tooth. and you measure this distance right here, and I have it at just under 25. If I had to interpolate, it's about 24.8 millimeters, but I would just round it off to 25.
Which tooth was that, Bruce?
This is number 14, tooth number 14. It's,
I do have-
go ahead.
I have a question. So in the figure, it shows that the crown height is from the bottom of the root to just kind of like where the cusp begins. So not including the pointy part.
Correct, not important. It's just that ridge.
Right. And so then in the picture, it's including the root all the way to the pointy part. So are the teachers only measuring to?
Yeah, they're measuring that actually, it depends upon how that's how it's positioned. That's positioned underneath the tooth. That measurement's okay.
Okay.
You're only measuring the extent of that ridge in A. That's called the mesostyle. You're not measuring the pointy parts at the top or the bottom of that image.
Yeah, I think this image is at the mesostyle. It's not at the tip of that point.
I agree with you. It's not the root. It looks like it, but it's not. You know, these are subtle nuances, and honestly,
at the end of the day, it won't matter for.
At the end of the day, whether it's a millimeter here or there, the pattern is so dramatic that the work that basically, you all want to do it the same way, and you want to do it the right way. But honestly, if one of the students does it and adds a pointy part in some of the teeth, it's not going to matter. And that's the whole concept of measurement variation anyway, which is a whole nother topic about how the process of science, but that's for another day.
Yeah, it's a whole other discussion that's great to have with the kids as well, for sure. But yeah, I think you're going to come up with the same outcome or the same conclusion, even if they're a millimeter off. So that's not going to be the end of the world in this case, for sure. Julie also placed, and I do have it in the slide deck at a later point, a video where Sean and I think it's Catalina's maybe in the video. They're going over measuring the teeth as well. And that video uses a digital caliper, which gives you a whole other vantage point. And then she also mentioned MorphoSource very briefly. We've got some information regarding that if you wanted to do this whole lab in a virtual digital fashion. And I'll get to that in just a little bit.
Parenthetically, in that YouTube, I think it's actually Julia, not Catalina.
Oh, thank you.
But
It's been a while since I've watched it.
for young aspiring scientists in your classes, Julia, in that video, is a fabulous role model. She's from Peru. She came and worked at the University of Florida on this project. She loved outreach. She's now a postdoc at Cambridge University, and next year she's going to be an assistant professor at California Institute of Technology. So if there's a wonderful story about Julia as a role model for particularly young women in science, girls in science, who might want to see a journey like Julia.
Great point. Okay, so I know we've got to get moving and put you in some labs. So last thing is that section on 28, the actual graph. And this is where you're going to plot the HI, that final measurement, that calculation, I should say, not measurement. That final calculation you took, the Hypsodony index, will get plotted on the y-axis of your graph, and time will be your x-axis in millions of years. And so one of the things you'll do after plotting those points is kind of bracket the ranges of the epochs. And I block them off going all the way up the graph paper so I can see this is the Eocene, this is the Miocene, so forth and so on. You're going to then use your colored pencils, green, orange, and yellow, to determine what was mostly forest dominated, what was mostly a mix, and what was mostly grass dominated. And you're going to kind of see what happens with horse evolution and the various species of horse over time through that process on the graph. One thing I would recommend as we go into the breakout rooms, which Brian will put you in momentarily, is that you all break up the measurements. Maybe someone handles teeth 1 through 3 or 1 through 4, so forth and so on. And someone takes, 4 through 8, so that you're all splitting up the work and then taking down the calculations together. Are there any questions before we do that? Again, Bruce mentioned, we'll be hopping in and out of all of the groups so that we can answer questions or help with any direction you might need. Are there any questions? Awesome. Okay, well, Brian, I think we're ready for breakout rooms.
I just want to confirm with you that we want to do 6 rooms of 3 to 4 participants per room. Does that sound right?
That sounds perfect.
Okay, then I'll go ahead and do it.
Thank you.
Oh, God.
For those of you that have not joined yet, you should see a pop-up on your screen asking you to join your respective breakout room. Eric, are you there?
Hey Bruce, when everyone's back, could you just go over quickly if all the teeth are from the same position in the mouth? Are they the same molar, and the importance of that, if that's important?
Yes.
I have a question, guys.
Sure.
My number 8 looks a little different than my partners in the group. Could it be that there's a mistake in my number 8 specifically? Because number 8 had a groove on the top and my number 8 does not have any groove whatsoever.
Can you see my number 8?
Yeah, I could. And can you see mine? It's lacking that ridge at the top. You see that ridge that you have, that little high point that you
Yeah.
have? I don't have it.
Okay. It might be a different one. Yeah.
Yeah, it's listed as number 8, but
Okay.
it's quite not the same.
All right.
But everything else worked.
Good. Did you see the pattern?
Yeah, of course.
Eric,
Good.
will you just do us a favor and send us an email with just letting us know so we can make sure to get you the right one?
I appreciate that, sure.
All right, so we realized that that was just a glimpse. Some of you may have been completely done. Some of you may have just been getting started, working, talking through it together, having some great conversations. But we wanted to talk through it and have that conversation with you as well. So again, welcome back. So like I said, that was just a little taste of just the first lesson. In the full curriculum guide for Chewing on Change, you'll find the background information, you'll find key vocabulary terms, standards that are aligned to this activity. You'll find teacher keys and guided questions for students, as well as assessments and quizzes for you to use with your students if you were to choose to. You can see all of these items in the Google folder that Stephanie shared earlier under lesson resources. But Stephanie is also putting that link once again for the Chewing on Change for you in the chat. So at this point, we want to open up the floor and sort of have a group discussion. We would love to hear from you. What are your questions on what you just did? What thoughts do you have? Any sort of reflections at this point? It could be how you envision using this in your classroom, or really anything else at this point that you'd like to share, or any other questions you'd like to pose to your students if you were in the classroom doing this activity, or just would like to bounce ideas off each other. So feel free to unmute yourself, and then we'll, like I said, open the floor to anyone that would like to start sharing.
Brian, Let's see, Jeanette asked me about the tooth, Jeanette, why don't you ask the question? I'll answer it.
Yeah, so is the tooth position in this set of teeth all the same one? So are they all the same molar across all the horses?
That is correct. They're all the upper first molar, and that's important because then they're the homologous position. That's a very important point.
So just to clarify, if someone were to measure the third molar of the upper tooth of a modern horse and the first molar of, like, say, Parahippus, your ratio could be thrown off. So knowing the tooth position is important.
Absolutely. The tooth vary, the tooth lengths and to a certain extent widths vary within an individual tooth row. So you have to always select the same tooth to measure. Otherwise, you're measuring and comparing apples to oranges, so to speak.
And same thing if you were to throw in a lower molar, a tooth from the lower jaw, that would be.
Oh my gosh, you don't want to do that. You got to do all the same. Now, a couple of you, well, excuse me, most of you know that tooth 13 seems to be mislabeled, and there may be an issue with some people's number 8. But anyway, the set still works. And when we send out the new sets to you for your classes, once you've determined how you're going to use them in your classes, we'll send you a set of 6 or 7 of these, and we'll send a replacement for the individual set that you have now. So you'll have a complete, full, and correct set for you to implement this in the classroom.
It looks like Latoya has a question. Go ahead, Latoya.
I do. Okay, when it comes to the graphing, I noticed that we needed to have those particular colors, green, orange, and yellow. And green was for forest dominated. Orange is a mix of forest and grassland, and then yellow is grasslands. Going back when we talked about the HI, if it's less than 1, they had a leafy diet. Greater than 1, it was a grassy diet. I'm trying to merge those two together to know how to do my graph. Once I plot it, how will I know which ones would be more?
So you're going to reference, let me go back. If you look at the screen up here, you're going to be referencing the epics that you've placed here based off slides, right? And you had made notations in your observations, bullets on whether the vegetation was more forested or more grassy. So you're utilizing this information here to help you essentially fill in the colors, kind of blocking or shading up the graph, those colors. Again, just like you said, green for forest, orange for mixed, yellow for grass.
Gotcha.
And then you can kind of see the overlay with the hypsodony changes, the greater than and less than HI numbers there.
Okay.
Good question.
Wonderful. Thank you.
Sure. So some other questions that you can start to have with your students is about variation and why maybe one species is quicker to adapt than others, and what happens if no adaptation happens, right? And then also even conversations about changes in climate over time and how that can be a driver for speciation events to occur. So some really good conversation there. And we wanted to ask you guys, like Brian mentioned, what questions you have looking at this through the eyes of a student, and what questions you might pose to your students if you were in the classroom at this moment talking with them about the subject.
Stephanie, Dr. Mendez had her hand raised.
Go ahead. Thank you.
He called me. No, I was just debating whether it'd be better to, I was writing it on the chat, and so I wouldn't interrupt you guys. Would it be better to use a line graph or a bar graph? Like to change the actual, for the students to actually see the different changes in color?
I typically just plot the points and make them like kind of bold, and then mark my eosine, my epics going up and going up.
Got it.
That's one way. I suppose you could make a line, a kind of across time if you wanted to see what happens with patterns, but because you've got some in the same epic, that becomes difficult because you'll see that you might have a couple points within the same range.
Got it.
Usually just plotting those dots, right, is sufficient to kind of visualize the changes.
Okay, perfect. Thank you.
Sure.
We didn't get to the point of graphing. I just calculated the HI. So in the calculations, were we really trying to see the change, right? How it increases?
That's
And pretty much.
Yes.
And then based on the greater or less than 1, then we can determine what they ate or what environment they had.
That's correct.
Okay. Can anybody show what their graph looked like, just to have an idea of?
Give me 1 second. I should be able to pull one up for you here. 1 second. Unless someone's faster than me. Someone might be faster than me.
It looked like Stephanie had hers up.
Okay, great. You want to let?
So yeah, we were able to graph in our group, and that's you can see the trends there as far as
Let me see where you are.
Are you able to spotlight that? Here, I'll unshare for a second too, though, so we can spotlight what you've got.
so I'm not sure how great you can see the dots, but you can see a trend, you know, as far as basically the trend is that way. Like the older it is, then the more likely the HI ratios to be less than 1. But yeah, there is one in the packet.
And Stephanie, in your experience pre, full immersion in the museum, how did you go about answering student questions about adaptations and that sort of thing? Like questions that maybe you don't have the background knowledge in paleo that you do now.
Great question. I mean, a lot of times I've always been kind of the school that if I don't know the answer, I'll say that to my kids and I'll say, let's look it up. And so together, and we were a 1-to-1 computer school before COVID and all of that happened. So we would hop on the computers and do a little searching to come up with the answers. I taught gifted honors IB classes for middle school science, and they were pretty astute. I would say a lot of my kids were able to draw connections. I did also have regular classes, and even the regular students with maybe a little bit of scaffolding could draw the connections and realize that there were clear changes in vegetation and there were clear climactic differences among those different geological time periods or epochs. And they could see the teeth as you line them up on the tables, that there was clear differences in those teeth sizes. We talked about the size of the species too quite a bit. Again, referencing the front of the guide where you've got a little baby horse. You can see the little baby horses in that first Eocene image. They were so small they could crawl underneath bushes or be hidden in trees and leafy materials to hide from predators, versus modern day horses, which would have a tough time doing that. So there was a lot of conversation about.
We lost you right here. No sound. Lost your sound.
Uh-oh.
You cut out a little bit regarding after your comment on modern horses not being able to hide in trees.
Yeah, so we would look at other adaptations from body size to the teeth changes and just draw conversation, comparison, contrast from those. And if I didn't know something or we didn't know something, we'd simply look it up, search it up. What's great is with SEFS, if that ever came to be in your case, always reach out to Brian and I, and we will put you in touch with experts too. So you have the great capability of bringing scientist experts into your classroom virtually or physically eventually. So that's always helpful. Oh, we did that one, yeah? Okay, so I have a question about the graph. So just now. Any other questions? Feedback, comments? And timing, I will just kind of also say that I don't know, I didn't get to go in every group at the beginning, but for the sake of time, sometimes I will have the kids break up the tooth set. So if they're in groups of 4, one student has a first few sets of teeth, the next student has the next batch, so forth and so on. They're all having an opportunity to practice measurement, to do math, which are key skills in science and using scientific tools that we teach them. But they're able to break up the workload a little bit for time's sake. This lesson, I usually would start the bell ringer would be the first exercise, and we would just do a little bit longer of a bell ringer, usually about 10 minutes. And then we would move right into the lab. Sometimes beforehand, I would, before the lesson, I would kind of preempt it with some of the background information about some of the concepts and terminology that they'll need to know for this. But usually it's a full day lesson, full class period. Sometimes even a class period and a half. All right. So then, again, that curriculum guide and whatnot is in that Google folder. I wanted to just quickly show you the other lessons in that curriculum guide. So you just sampled exploring the geologic timescale via changes in fossilized horse teeth in response to the evolution of plants, right? There are 2 other lessons in there which are dynamite: examining intra-species variation and changes in a single horse population, and also proposing changes to orthogenesis and communicating evolution in museums. I tended in middle school to do lessons 1 and 3. Students really like to do this concept of orthogenesis versus phylogenesis. And there's a cool letter where a museum curator wants to redo their exhibit. And so the students have to figure out how to correctly update the exhibit based off of new scientific information. And it's a great way of connecting a lot of the nature of science standards with the evolution standards that we teach. So those lessons we're not going to go into for sake of time, but again, you have all information to walk you through those within that guide. And that is bringing me to the next slide. This was referenced briefly by Dr. Bokor. There is, Jeanette, did you have a question? I'm sorry. I think I just saw a hand up.
Yeah, I was just gonna ask you to define orthogenesis, as I don't know if that is used in middle school or high school curriculum.
Okay, good point. So orthogenesis is the concept of a linear evolution. And we see that probably most commonly, which is a misconception on all accounts with regard to human evolution. And you know that particular image I'm talking about with hominids. In the case of orthogenesis, it's linear. And phylogenesis is more like a tree-like or branching concept. And you have speciation and various species happening at the same time. And Bruce, if there's other information you want to share there or clarify, please do so. But that's how I usually explain it to my kids.
No problem. Ortho means straight. Genesis means origin. So it's basically a straight line evolution from ancestor to descendant, which is a theoretical framework for evolution that was developed 150 years ago, but we know is wrong. But some textbooks and some older museum exhibits still portray horse evolution as orthogenesis, and this lesson dispels that misconception. But Stephanie, you explained it just fine.
Okay, thank you. Okay, so what's kind of nice is whether you are physically teaching in the class and you happen to have the 3D print models, or heaven forbid, you've got a pandemic on your hands, you can take this lab virtual. If your students are at home and they don't have access to the 3D print sets, or you don't have a 3D printer, or you don't have the sets available, you can go on a site called MorphoSource. And Julie had mentioned that Sean, one of the previous graduate students of Bruce's, had digitally taken all the teeth and digitized them essentially. So these teeth are uploaded onto MorphoSource. It's a free site, and you can access the teeth there. There is a video tutorial that shows you how to take measurements, and you can see that little dot there and the little dot there. So students can take measurements directly from the site and do it from a digital perspective instead. There's also a link to the video on how to use digital calipers that Dr. Bokor had put in right here for you. And then there's a really interesting, and I'm going to click on it for just a second. There's an interesting example of someone who elected to take the files from MorphoSource and create their own kind of virtual lab or scavenger hunt, if you will. And this one happens to be on hips. So they uploaded those files and the kids do all their measurement. All the questions are loaded in here. So it's kind of a one-stop shop for a lab. And you have access to all of these materials and tools as well. So I just wanted to point that out to you that you can click on these links in your PDF and it'll take you to those sites should you want to see the digital version of the lab. So with that, I think we are ready to hear from our next speaker, one of my very favorite people of all time. This is, and you've met her, but I'll reintroduce, PhD candidate, Dr. Almost, Jeanette Perlow, who will be helping us transition content just a bit in anticipation of the tour of the Mammoth exhibit we're going to take at the Frost today. So her spark is entitled Stompin' Through the Marshes, a look at gomphotheres from North Central Florida. So we're kind of switching gears for courses just a little bit to one of the other organisms that were out in some of those images we were looking at. Jeanette, I'm going to let you take it away.
Thanks, Stephanie. I moved outside in hopes that the internet is more stable out here, but please let me know if the background noise is too loud. I forgot my headphones at home. So let me share my screen. And if I go into presentation mode, this should work. So thanks, Stephanie, for that introduction. No pressure. So I started with Bruce several years ago, and I had no background in paleo. So I approached this from a very similar background as your students and yourself if you don't have a background in paleo, and that's I absolutely hated paleontology until I went to the Montbrook site and did my first dig and found my first fossil. And then I started scheming on how to convince Bruce that he had to hire me in some capacity. Luckily, I somehow convinced him that he needed me as his grad student. And 5-6 years later, here I am working on writing my dissertation. So this image that you see here is on the Montbrook dig site, which is in Williston, Florida. So about 5 hours north, maybe 6 hours north of Miami. And it is a private property where they mine sand, and the owners found this massive trove of fossils, including elephant fossils. So this is from the late Miocene to the Pliocene. So if you look at your guide, you'll see that's about 5 to 6 million years ago. So it straddles this really interesting geologic time. Is the background noise too much? Okay. So this straddles a really interesting time in Florida when Florida was above water. So ocean sea levels were lower. Then they were a little bit higher than they are now. So Montbrook, even though it's in the middle of the state, was actually closer to the coastline than it would be now. So this site is near and dear to my heart. And pictured here, we have several of our volunteers, actually all of our volunteers and a couple staff. The site is mainly dug and operated by our volunteer paleontologists, which are community members, retirees, K-12 educators, and even sometimes students. So we start bringing out volunteers as early as 15 years old. And everyone in the blue shirt are high school students or teachers in a paleo club, a fossil club that was established here in Gainesville at Gainesville High with Maggie Paxton and Lee Larson in the background. So let's talk a little bit about this. And so The Frost Museum has mammoths and mastodons, mostly mammoths, I believe, which we'll talk about. I study a different group called gomphotheres. Thank you for sharing that chat, Stephanie. We are starting up the dig site, so if you're interested in volunteering at the site, sign up, come dig with us. So a little bit on proboscidean evolution. Proboscideans are anything that is related to elephants. And just a quick fact, sometimes we refer to elephants as pachyderms. Pachyderms actually corresponds to anything with a thick skin. So a rhino can be considered a pachyderm. A hippo can be considered a pachyderm. So sometimes we use pachyderm interchangeably with elephants or proboscideans. That's just a fun fact for kids to know, for students to know, that pachyderm does not always correspond to elephants, but proboscideans corresponds to anything within the elephant group. So elephants have a wide history. They've been around for millions of years and evolved in Africa. And currently we only have 3 species of elephants left. That's the African elephant, both the savanna and the forest elephant. So there's 2 elephants in Africa, and the Asian elephant, which is found in India and Southeast Asia. But through time, we've had this huge diversity of elephants, including dinotheres, with this unique set of tusks coming out of their lower jaws. So modern elephants now have tusks coming out of their upper jaws, and they're actually modified incisors. So if you think about the incisors in your teeth, in elephants, they have modified, similar to narwhals, to come out into this exaggerated display, which could be used for both display and useful tools for food and protection. Mammoths here, the Mammuthus group, have these huge, huge tusks. Modern elephants, Loxodonta, and my favorite group, Gomphotherium, which has both upper tusks and lower tusks. And even the lower tusks are also modified incisors. So a little bit on where elephants originated. They began in Africa in the Paleocene, which is older than the Eocene, which is in your workbook. So if you looked up geologic time in online, you'll see that the Paleocene is older. And in this figure in the top left, this is showing the proposed movement of the mammoth group from Africa into North America. So, but it mimics elephant movements, migration and movement into North America from evolution in Africa, where they started in Africa, moved north into the Sahara and out into Europe, and then into Asia, across the Bering Strait into North America. And elephants arrived in North America in 2 pulses. Around 16.5 million years ago, we had Gomphotherium arrive. And then about 15 million years ago, we had another set of elephants move in. And the group Gomphotherium is represented here at the bottom left, showing the diversity within that group. We have the Gomphotherium species, Rhynchotherium, which is a group I study, Cuvironeus, and Nodiomastodon. Sorry, it's a little bit louder than I expected. I don't know if you guys can hear all of that. And so elephants are this really unique group in that they spread out throughout the world to all the major continents except Australia and Antarctica, but you can find them down to the tip of South America. So I have this wild idea of how to get to Antarctica, but we won't say what it is because Bruce is back and I want my PhD. All right, so a little bit on the teeth, which is really what I focus on. If you remember in the previous slides, a couple slides back, there was the one elephant that had the recurved lower tusks, the Dinotherium. This is what its teeth look like. So even an elephant, did I freeze or am I still okay? even though it's an elephant, if we look at the other elephant teeth on this slide, they're very different. So Dinotherium was unique in that, unlike modern and older elephants, it did not have tooth replacement through its lifetime. Whereas other elephant groups, so like modern elephants, gomphotheres, mammoths, mastodons, go through 6 teeth in their lifetime. So similar to sharks, elephants have horizontal tooth replacement, where we have vertical tooth replacement, and we go through 2 sets of teeth in our lifetime. They fall out and a new tooth comes in. Elephants have teeth in the back of their jaw that grows up and pushes the forwardmost tooth out. And so through their lifetime, to deal with that abrasive forage that they're eating, the grasses and the leaves that they're eating and are wearing down their teeth, instead of dying at a young age of no teeth, they're actually modifying how their teeth are replaced so that they can live longer lives and eat more of that abrasive material. So with horses, they evolve taller, long-living teeth to deal with that abrasive material. Elephants evolved tooth replacement through their lifetime. So gomphotheres have this more bumpy tooth. African elephants have this unique diamond shape. Asian elephants, as you'll see, has a very compressed lateral tooth plates, similar to mammoths. And if we look at modern literature, we can see that the Asian elephant is more closely related to mammoths than any other elephant groups. And you can see that reflected in their teeth. All right, so a little bit on the Montbrook site. We've collected over 30 jackets of just skulls and mandibles. So at least within that site, we have at least 30 individual elephants, which is very unique. Normally you find 1 or 2 individuals. This site is chock full. And as I mentioned, it's about 5 to 6 million years old. And we have at least 2 elephants represented at the site. So mastodons, which are in the genus Mammoth, and gomphotheres, probably Rhynchotherium, but my dissertation focuses on trying to define which other elephants are at the site. So stay tuned in the next couple months. No pressure. All right. So a little bit more on gomphotheres. They are characterized by this really long lower jaw, as you can see here, with their lower tusks anchored midway up the jaw, but they have this very long lower jaw. And their tusks also have this enamel band. So this darker color here is enamel, very similar to the enamel on our teeth. And then the white part, the characteristic ivory of a elephant tusk, is actually the dentin of the tooth. So it's not all enamel. And so having this characteristic enamel band is definitive for certain species. So knowing that that's enamel, we can start narrowing down the type of elephant that it is. They also had long, low skulls that essentially match these lower jaws. And as you can see here, this back tooth, the outline here, the spotted outline that we have here, that is showing where that replacement tooth is starting to form in the lower jaw, or the crypt, and is starting to move forward. And as the teeth wear and start moving forward, you start seeing that the tall crowns of those teeth start getting lower and lower and more worn. And eventually that forwardmost tooth will get spit out and fall out. And sometimes you find those, and we can determine what tooth it is and how old that tooth is of an individual animal's age based on how worn that tooth is. So my current research, like I said, is determining the species at the Montbrook site. I also do stable isotope analysis, which I'll describe more in a second, but I want to understand how the ecosystem at Montbrook was partitioned between all of the mega herbivores. So apart from the elephants, we also had rhinos, we had horses, we had camels, we had so many other herbivores. So how is this one environment able to sustain so many herbivores that actually require a lot of food to keep them alive? I'm also looking at the population dynamics of the site. So trying to understand what species are present, how that site was actually accumulated. Did we have a like, was there a giant flood killed off all the elephants, or did this happen over a long period of time? And how those elephant populations were actually structured. Do we see a similar structure to where elephants now, where it's matriarchal, or do we see a different population structure? And how big were these animals? Is my internet holding up, Steph?
Sorry, you cut in and out just a tiny bit, but I think the closed captioning might have kept up with you.
Okay, good. So here's one of my favorite specimens that we have on site. This is one of those lower jaws, and the tusks are missing, which would be at the far right, but you have this very long elongated symphysis or chin. And interestingly enough, we also have a turtle that is attached to the jaw. I won't tell you why. I'm going to let you think about that, and you're welcome to ask me these questions. But this is one of my favorite pieces because it is such a thought piece as to why there is an elephant with a turtle stuck between its teeth. I believe it needs to floss. All right, so a little bit on the stable isotope analysis. Looking at we are what we eat. So similar to horses, if you're eating grasses, that's going to be reflected in the chemical analysis that makes up your tissues. If you're eating leaves, that is also reflected in our tissues, because we are pulling our nutrients from the food that we're eating. So one way that we have figured out how to determine what ancient animals we're eating, since we can't go back in time and watch them do it, is by looking at the chemical analysis in their remains. So in more modern species, you can look at DNA and figure out how they're related. But DNA can only give us information up to so many thousand years. It doesn't go back millions of years. So we have to figure out other ways to determine how animals are related and what they're eating. So one way that was established, and Bruce is well aware of this as he's also a pioneer in stable isotope analysis, is to look at the ratio between heavy isotopes. So this becomes a little chemistry heavy. Heavy isotopes to the lighter isotopes. So I use carbon and oxygen that is preserved into the teeth. And I use teeth, specifically the enamel, because the enamel is so hard that it does not often get replaced by other minerals around it as the tooth is fossilizing. So we're able to use the actual minerals that were used to create the tooth when the animal was alive, and then determine what they were eating from there. So with carbon, depending on how negative it is, if it's on the more negative side, more negative, say -10, these are going to be your heavily browsing animals. So they're eating lots of grass, lots of leaves, lots of shrubs. Anything more positive, so 0 to positive numbers, are going to be your grazers. They're eating more of the grasses and less of the leaves. So now you start seeing two types of herbivores that can live in the same areas but are eating two different types of food and not outcompeting each other. And then the fun part is the mixed feeders that are able to eat both grasses and leaves. So they are able to adapt to changes in their environment. And if there's not enough grass, they can also eat some leaves, eat some bark, some twigs. And so for preliminary research so far, I'm still working on finishing this up. Amebelodon is a type of elephant. Gomphotherium is a type of elephant, and Mastodon here. And if we look at the colors, they are plotting in the negative area, except for Gomphotherium. Gomphotherium here is plotting kind of all over. It's this darker brown. So Gomphotherium is a mixed feeder. It's able to eat grasses and it's able to eat leaves. Whereas if we look at, where is a good one? Like Nanopus here, this horse, it is in the more negative side. So it's eating more of the grasses. So you're starting to see that separation of feeding in Florida during the late Miocene. And I collect these samples by drilling just a little bit of powder off the side of the tooth and running that through a mass spectrometer. And our lab tech actually does that work and gives me all of the values instead of me trying to figure out the values, we get that done through the geology department, which is really helpful. We also look at microwear analysis. You can compare your chemical analysis to the actual physical properties on the tooth. So the teeth, the food that we eat is leaving marks in our teeth. So by looking at the wear under a microscope, we can start seeing the pits and scratches that our food has left on our teeth. And it's usually indicative of the heavier brows, whereas the scratches is more for grasses. So you can compare that, and if you see an animal that is allegedly very brows heavy based on your chemical analysis, and you see similar evidence from the scratches and pits, you can you have more evidence showing that they were browsers. And I think I am running close to time. Do I have, how much time do I have, Steph?
I've got you till 10:30, so you're
Okay, perfect. So here's just some fun pictures of fossils. So this is a lower jaw of an adult elephant from Montbrook. We know it's an adult based on the teeth that are present. So again, those teeth are growing throughout their lifetime. And as new teeth are replacing, we can determine how old the individual animal was. And this is in comparison to modern elephants. So looking at modern elephants, we determined that at 20 years old, an individual elephant had a certain tooth in place. So we have backtracked and used that same analogy in ancient elephants, since we can't go back and actually determine that age. And this is in comparison to a baby mastodon jaw. Sorry, I'm stuck on mammoths today. Here's its little baby tusk, which I find darling. And when I'm feeling a little sad about my work, I go look at the baby tusks in the collection because they're adorable. And right here, you see this hole. I don't know how well you can see this hole, but that very first molar, its deciduous premolar 2, has fallen out. Because this area is not filled in by bone, we know that the tooth has fallen out after burial. So at some point that tooth fell out, it was not, the bone wasn't remodeled. And the third premolar is not at the front of the tooth. So at some point, this tooth got lost. So based on the evidence of what teeth are present, we know this is a young animal, maybe 2 years old at the oldest. And back here, this darker brown material is the first molar that is developing in the back of the jaw and will eventually replace these other teeth. So based on the teeth and the amount of wear, we can determine how old an individual elephant was. And with that, I just want to say thank you. And please let me know if you have any questions. Here's just one of my favorite things about Montbrook is all of the volunteers and how happy they are, and they've found the majority of the really cool specimens. So I like to highlight them, and a shout out to the owners of the site, the Hodges. So yeah, let me know if you have any questions.
Thank you so much, Jeanette. And
Yeah.
I just want to echo her thoughts. If you have any questions, we're just going to leave the floor open, give you some space to think about her talk. And if you have any questions, feel free to unmute, jump right in and ask her.
Jeanette, can you explain what a plaster jacket is?
Yeah, certainly. So a plaster jacket is literally what it's saying. It's made out of plaster. So like when you break your bone, you go and get a cast wrapped around your broken arm per se. And we use that same material, the same bandages and plaster to protect the bones in the field. So when we find a skull or a jaw or a leg bone out in the field, we want to protect it to bring it back to the lab so that we can clean it up and harden it with glue so that we can use it for research or for showcasing in the museum. And the best way to do that is to cover it in this plaster material with the surrounding dirt around it to keep it nice and protected. And then we drive it back to the museum, and then another group of dedicated volunteers will start cleaning that, gluing them all back together. I've seen our volunteers take bags of broken turtle shell and put together an entire turtle shell from broken pieces. So if you like puzzles, That's definitely the job for you. I don't have that kind of patience. And the plaster part's the most fun, to get paid to play in the dirt and get dirty. I think is the best part. And students love doing the plaster jackets as well.
As we study the change in diet, what is the most important thing? Why do you think the change in diet was so important to these animals changing or evolving? I mean, what does grass do that the leaves
That's
and
a
the
really
tree
good
does not do?
question. And yeah, again, really good question. So if we think about what happens, temperature and climate has a huge impact on our environment. And so we see that happening now at a very rapid scale, and things are having a hard time adjusting, even the grasses and the trees. But prior to human involvement, climate change happens in a cyclical manner, right? Like it's still happening through time. And so as it's happening in a slower manner, plants are starting to adapt, and you start seeing that change from an area that is warmer, moister, more tropical. You have all of these tropical plants and trees to a drier, more arid condition. So you need plants that can handle less, needing less water. So you start seeing a change in the type of plants. And with that, you also see a change in nutrients within the plants. So leaves that are being renewed annually have so many nutrients and are much more nutritious to animals, versus grasses are usually more nutrient rich. If you grow any livestock, horses or cows, you know that certain feed is more nutritious than other feed. So that is happening. So with elephants that are grazers, they need to eat a large abundance of feed throughout the day, of grass throughout the day, to get the same amount of nutrients that, say, a leaf eater would be getting.
Thank you.
Yeah, of course.
So what is the explanation for the total inside the elephant's mouth?
Oh, that's a great, what ideas do you have? I can tell you the answer, but I prefer hearing other people's ideas first. What is your explanation for a turtle in a horse's mouth, in an elephant's mouth?
The elephant died, and then there was a flood, and the turtle was swimming and got stuck.
Well, yes, you are correct. That is most likely the correct answer. And good for you. And I'm very happy for you. However, I have a fable for specifically teenagers. So the site is heavy in teenage elephants. Again, I mentioned that we can identify how old an individual elephant was based on the teeth present. And if we look at modern elephants, teenage male elephants get kicked out of the herd because they start, talking back to the mom and have more testosterone and start flexing their muscle. And so they get kicked out of the herd. And so they're more at risk of dying. When you first get kicked out, if you didn't figure out how to live by learning from your aunts and siblings, you have a harder time surviving. So these young male elephants in modern elephants are creating these loose teenage male gangs. So if you imagine these testosterone-filled teenage boys running around the savannas, I will, as middle school and high school teachers, I'll let you think about that.
I was just thinking about it. Can we do that?
Yeah.
Can we just kick the teenagers out? I have a teenager myself. So.
I agree sometimes. So now you have these testosterone-fueled young male elephants that are, fighting for dominance, or starting to, fight against the older males, trying to impress the ladies. So my fable for lessons for teenage boys is that, we had this teenage group of elephants at Montbrook. We have examples of turtle fossils that have circular imprints on the shell. Some could say they look like footprints. This is all, a popular story that I like to use. There's no scientific basis to it yet. But there's this, you know, it looks like a footprint. So I imagine these testosterone fueled young male elephants kind of running around playing whack-a-turtle like you would whack-a-mole and just stomping on all these turtles in Montbrook. There's tons of turtle fossils. And at one point, this one turtle, some could call him a ninja turtle, decided to, you know, take this matter into its own hands and save his brethren by choking out this mean elephant male teenager and sacrifice himself for his kind. But the lesson learned is don't be a jerk and stomp on other people, and or you get choked out by an elephant. And that will be a chapter in my dissertation, Bruce, if you did not know. Jason, our fossil preparator, will be illustrating it, and I'm hoping to make a children's book out of that. And that is the fun story that I share with students about not being jerks and being mean to the lowly turtles and no bullying. But the real story is the elephant died, a turtle got stuck under it, they preserved together, and now we have this wonderful fossil that leaves a lot for the imagination.
And with that, I think we're going to move on, but Jeanette is still here. If you have any questions, feel free to write her in the chat. I'm sure she'd be more than happy to answer any questions that you have. We are going to move forward by hearing from Kate, who's going to lead us through the Frost lesson, Mammoths on Ice Age Giants. So Kate, please take it away.
Hi, everyone. I've gotten to talk to some of you. I'm excited to talk to the rest of you. My name is Kate Carter. I'm the Director of Science Communication at the Philip and Frost Museum of Science. I have lived in Miami for all of 5.5 months. I'm coming up on my 6th-month anniversary in February, so I'm really excited to be here. And as I was saying on Thursday, one of the things that we're hoping to do as a museum is really integrate more with Miami-Dade public schools. So this is one of several initiatives that we're working on to try and really be more involved in the schools. We haven't had a lot of time with the pandemic, or we haven't had a lot of space to be able to kind of meet. We haven't had a lot of field trips recently, as we all know. But that's kind of something that we're hoping that will come back in 2022. So before we get started, I'm going to take you on a tour of the Mammoth exhibition. I want you to kind of think about your ideal field trip experience to a science museum. And you can either think about it from the perspective of a student or a perspective of an educator, because I know when you think about it from an educator's perspective, you have to think, oh my gosh, they're going to be in different places and I need to have chaperones, and the chaperones need to know what to do. And there are a lot of things that go on in your head as an educator. But I want you to think about, because we know that a field trip, especially to an informal science learning institution, is supposed to do more than just recapitulate what's in the classroom. But at the same time, it needs to fit with what's happening in the classroom. It needs to feel aligned. It needs to feel like the students get maybe the same ideas, but in a new way, or they need to be able to kind of rediscover through hands-on learning. So take about 30 seconds. Feel free to, if you are a sharer, feel free to unmute yourself and give us some details about your ideal museum experience. Or if not, just write them down. We will. Does anybody have a childhood memory of visiting a museum that was amazing for them?
I can say something. I think ideally as a teacher, definitely doing hands-on activities, for the students and reinforcing whatever science concepts I've taught, and just maybe leading them in groups through different stations where they can, they have activities and it's guided instead of them running around everywhere. Yeah.
Yes. Oh, drawing parts of the exhibit in a sketchbook with your dad. That's awesome, Stephanie. Where was that?
I used to live in St. Louis. I grew up in St. Louis. That was a special time. My dad and I would go to the museums and hang out and sketch.
Oh, well, that's the American Museum of Natural History is amazing. That's awesome, Chris. So as you're thinking of that, and I kind of want these experiences to kind of frame our visit today, I'm gonna start sharing my screen. I wish you were all at the Frost so that I could take you on a tour in person, but I will be sharing some ways for your class to visit us. For those of you who haven't visited Frost Science in a while, we are at a brand new location. We're coming up on our 5-year anniversary there. So we opened in 2017, and we are right downtown. And we have a lot of new things happening. I say this having lived here 5 months, just go with me. But we have a lot of new things happening, and I'll tell you a little bit about it. One thing in particular we have right now is we have another evolution exhibit called Skin, Living Armor, Evolving Identity. It was developed by the California Academy of Sciences out in San Francisco. And it looks at evolutionary adaptations in the skin, as well as helps develop a scientific scaffolding for talking about conversation about skin color. So helping your students have the science information. So we've gotten a lot of really positive feedback about that, and we do have educator resources for helping guide those students. So can everybody see the YouTube video? All right, let's get started. So we're downstairs in the atrium. I figured I'd give you a little mini tour. The Mammoth exhibition is up on the 4th floor. So this is gonna go fast. And I apologize. It turns out that I cannot walk steady even with a selfie stick.
Kate, can you expand it a little bit bigger?
Of course.
Awesome.
So we are up on the 2nd floor. The 2nd and 3rd floor holds our human body exhibit, the Me Lab. Then we're coming up to the 4th floor, and here is Mammoth Ice Age Giants. So this exhibition opened in November, so it's quite new. It opened just before Thanksgiving, and it will be here for 2 years. The specimen is on loan, so we won't have it forever, but hopefully many of you will get a chance to see it. And the other reason I did this is to show you partially the view, but let's look over at the water here. The sun was in my eyes when I was filming it, so I was trying really hard. So we have a lovely tropical landscape. But now that we are familiar with the names of the epochs, I want you to think about what this landscape might have looked like in the Pleistocene. So you've gotten your sketches of the Pleistocene. Now, obviously, we didn't have snow here. But what are some things that people might expect this would have looked like 10, 20,000 years ago, kind of at the tail end of the Pleistocene? There are no wrong answers here. What might you think?
Marsh.
Marsh, yeah. So definitely lower sea level. In fact, you could stroll to Miami Beach or Virginia Key. There was no water there. Absolutely. What else?
More insects, a lot more insects, flying things, hot. I don't know.
Yeah, so definitely no modern mosquito control technology, which I so dearly appreciate. Do we think it would have been, with what you have seen already, do we think it would have been a lot Do you think it would have been warmer or colder? And do you think it would have been wetter or drier?
More humid and wetter?
So based on the reconstructions, it would probably have been a little bit cooler and a little bit drier. When I say a little bit cooler, I don't mean that we would have frozen tundra like we see when we talk a lot about the Ice Age, but it would have been slightly cooler. You may not have so many 75-degree days in January. And it also would have been a little drier. So not as much rainfall, especially that kind of late summer rainfall that we see. So let's head into the exhibition. Well, I guess one more point I want to make is we have a woolly mammoth exhibition. Now, just like there is no frozen tundra in Miami, there are unfortunately no woolly mammoths in Miami. However, and this is something really important for your students to know, there were actually mammoths in Miami. They just weren't quite as fluffy. The Columbian mammoth, which is another species of mammoth, did exist in South Florida during this time. So you can tell your students that there were mammoths, as well as many of the other Ice Age fauna that you'll see, Ice Age animals that you'll see inside. We just didn't have cold enough climates to need fur. So what I'm going to do is I'm going to give you a quick walk around the space with the goal of, since we can't be physically there, just to kind of get you oriented to where everything is. And then we'll go through and we'll talk about each component individually. You know, feel free to ask questions, feel free to make comments. This is a tour. So if this were in a real space, I would expect you would have questions. I would expect you would want to know more about things. So feel free to interrupt me, feel free to ask questions in the chat, or feel free to unmute yourself and ask questions. If I don't know the answer, there's a chance that somebody else in this room will know the answer. So we're going to go ahead and head inside. And there we go. So it's a small exhibition for those of you who have been in the space. It replaced our design lab, which was more of our kind of engineering space. And inside the exhibition, we have several fossils of both mammoths, mastodons, and some of their Ice Age relatives, and some of the other animals that lived alongside them. We have information about the relationship between different groups of mammoths, as well as the climate. And we finally have the specimen itself. So I'm going to start here. I'm going to stop the video. This is, for those of you who, now that we've done the chewing on change activity, there should be a lot of overlap between the graphing activity you just did and the colors of the wall here. So similarly to what you just did with the chewing on change activity, the background color of this phylogeny that you see corresponds to the temperatures that we see. These are derived from oxygen isotopes, but very similar overall. What are some observations that people make? Where is clearly the warmest time, the brightest red? Can people see the numbers? The numbers are at the bottom of the screen down here. Oh. Does someone want to point out where they are, like relative to, if you can't see the actual numbers? Oh, someone put in the chat. Far left, hottest, perfect. And then if you look, continuing on here, sorry, it's hard for me to see the entire video on the screen and see people and see the chat. I'm not yet gifted at that. Then you can see that the end of the Pleistocene is one of the coldest periods. So I'm going to kind of briefly go through, Jeanette did a great job discussing gomphotheres. I'm going to point out that one of the internal nodes represents a minority viewpoint, roughly between gomphotheres and mastodons, but we can discuss it later if need be. And the other thing that I want to point out, I'm going to make it smaller so that I can see everything at the same time, is the relationship between mammoths, Asian elephants, and African elephants. So can everyone see the phylogeny? Yes? No? Okay. Based on the phylogeny of mammoths, Asian elephants, and African elephants, what two species are more closely related?
Asian and African elephant?
Well, let's see. So the African elephant, I'm guessing can you see my cursor when I share screen? Yes, okay. So the African elephant diverged back here. Yeah, and the Asian and the woolly mammoths diverged later. So one of the things that I think is really shocking is that even though we think of the Asian and the African elephant looking quite similar, in the woolly mammoth and the Asian elephant are more closely related. So let's go to what I think many of you came here for and look at the specimen itself. So we're going to start by looking at a photo of the mammoth inside its skeleton, and then we will start exploring the specimen itself. As you're leading your students around, they'll probably have questions about some of its morphology or some of the way that its bones look. Are there any weird things that you notice about our mammoths as we're zooming in, about anything that is surprising to you?
Are they walking in their tippy toes?
They're walking on their tippy toes, absolutely. So that is not a mistake. That is definitely how mammoths walked. And despite it being something that it would cause us a lot of pain on our calf muscles if we did that, that was in fact an adaptation. Are there any other things that you notice about the mammoths that are weird? I was like zooming in on the feet there. Are there any other things that you have questions about or notice about the animal?
Quick question, even though they were walking on their toes, wasn't it like a fat pad or something underneath
Exactly.
the heel? Gotcha, okay.
Yep. So now we'll go to the specimen itself.
Okay, we have a question in the chat. What environmental advantage does that have for them to walk on tippy toes?
So as they're saying, it's about the fat pad. So, but it also allowed them to have a little bit more control of their environment, to have a little bit more sure footing.
Yeah, so that fat is used to like lessen the stress, the mechanical stress and the energy to walk. So if you think about like sneakers that have like for, you know, us older individuals that had the sneakers that you could pump up with air that supposedly give you more lift or more bounce when you were walking. So elephants have that fat pad built in that works as a spring. So when they put the step down with gravity, gravity helps them put their foot down. That spring works in the opposite direction to help them lift their foot and use less energy as they're walking. And because they are such large migratory animals, they need to be able to spend the least amount of energy while walking, so that that fatty pad developed as the animals got larger. Sorry to jump in, Kate.
I
No
love that
worries. Thank you for
explanation.
answering.
I'm sorry. I was thinking, what about if the picture that we see right behind it, if they're actually stepping on snow, like fat tissue also, I'm assuming will cause some sort of insulation for them.
Yeah, I don't know
Yeah.
if they've looked into the literature. Go ahead, Kate, if you know more.
No, it definitely does have some insulation. The other kind of cold adapted thing is that mammoths have quite small ears relative to modern elephants. So when you think about a modern elephant, maybe you think about the trunk first, and then you think about the giant ears, which are very useful for those animals in warm climates. But mammoths obviously have very different adaptations because they have to exist in a cooler climate. So I'm going to kind of continue going through the skeleton here. Any other observations or questions? This is a skeleton comprised of individuals of multiple ages. So it's not one single individual, but it's several individuals that are roughly the same size. Anywhere from about 20 to 45 years old. So many different individuals. So obviously I went through the barrier to be able to film up close to kind of show you this, but hopefully that will, yeah. So
Their lower jaw was tiny, huh?
let's see. Yeah, the lower jaw was not as large as relatively as some animals, but it's really focused on the molars. So if you think about what you use your different teeth for, if you're eating grass, if you're a grazer, then you don't necessarily have to spend a lot of time kind of preparing the food. So it was very back tooth focused.
I see.
As you can see, we don't have a lot of space for anything other than the molars. And to kind of pick up on what Jeanette was saying about the teeth, elephants would not have all of the teeth in their mouth at the same time. Similar to horses, we're going to tie everything back together. When you eat a lot of silicate heavy material, it does not do great things to your teeth. So you have a lot of wear on your teeth. And elephants developed different adaptations from horses, some of the same ones, but also different, to really contend with that wear. And one of the things that they do is they space out the eruption of their teeth. So it would be like if we were getting our wisdom tooth at our 60th birthday, when maybe we actually have wisdom, as opposed to our 18th birthday. So much longer spacing. Any other observations about the mammoth?
Kate, you've got a couple in the chat box, but I did want to, or just kind of reiterate. So comparatively to the horse's teeth, what happens with the horse's teeth over time versus the mastodon, or the mammoth, who is basically pushing a tooth out and a new tooth is taking its place? What's happening with the horse tooth over time?
So the horse tooth, those giant teeth you measured will start wearing down over time. But the horse tooth will still have a little bit. So I can show you a mammoth tooth that's worn in just a second, but it will show a lovely kind of just like a flat surface whereas the horse tooth will continue to have some amount of relief on it. Some
Excellent.
amount.
We've got a couple questions in the chat box.
Yeah.
Catherine wanted to know, talk a little bit about the back legs versus the front legs. It appeared that the back legs were a little longer than the front. And why would that be helpful morphologically for them?
I do not know the answer to that question. So if somebody else knows, you can jump in there. Let's take a look zoomed out.
I think biomechanically that just helps with movement and stress and the food that they're reaching. So if you think about like a giraffe, when it's trying to get water, it's very high off the ground, so it's having a hard time. With elephants having that back end kind of extended, they're still able to reach the ground even with their tusks. So it helps with center of gravity. Think about that heavy skull and those heavy teeth and the trunk and all of that muscle to chew. You need to kind of counterbalance some of that movement, which is seen also in the vertebral column and muscle attachment. So it's all kind of working together with that situation. And I think one of hyenas also have a higher rear end than their front end. And I believe there's literature on why that's helpful to their success.
Thank you. Bruce wants to know, Kate, about the skeleton, or the majority of the skeleton, I suppose. Where is it from? Where was it located?
So this one was excavated from Russia, northern Russia. So they're all from roughly the same location. This was donated by a collector to the museum. So some of the exact information about sites and locations are unknown to us, but most of the skeleton is from Russia, or all of the skeleton, we think. Any other questions about the mammoth itself? I want to be mindful of time.
Okay, so when you're ready, feel free to jump into the lesson itself and share additional resources that you have on some of the information that you've shared.
Yeah, absolutely. So I will end by showing one of my last thing, showing one of my favorite elements of this exhibition is this. Look at the teeth one more time. We do have, now this is not a real specimen, it is a cast of baby Dima, which is a 7 to 8 month old mammoth. Most of the time, what I think is really cool is most of the time when you are a paleontologist, you find bone and teeth. More teeth than bone, but you find stuff that is hard that preserves. And what's really great about baby Dima is that they actually found some of the soft tissue remains. So for example, they were able to find milk in the animal's stomach, which I think is great. They were able to see information about the hair and the skin, which will help scientists really be able to understand kind of really some things about mammoths that we're not able to understand. Now, baby Dima was found many years ago. It was found in the 70s, but there have been a couple of other infant mammoths, so even younger than this one, found in the last decade, which have been kind of, now that we know how valuable they are, they have been able to do things like sequence DNA. So that's really exciting. All right. So I'm going to stop sharing here. And I can make the video, I can share the video with everyone. I would ask that you don't share it with anyone else. I did not ask permission about whether or not I could share it. And then I'm going to talk to you a little bit about the resources we have. And then I'm going to take you through one of our lessons. So all right, So first of all, for those of you that don't know, we do offer free membership to educators. So if you are interested in seeing the frost for yourself, we would strongly recommend that you come and visit us. This does include free admission, and you also get access to a planetarium show. And there is a potential for you to bring, you can bring other people on select occasions. So it won't be enough to get your entire class in, but we do offer free membership. It's pretty easy. If you have questions, you can feel free to email me, but we definitely encourage you to come. We are offering in-person field trips. I know that that is something that is, who knows? And by completing this PD, we will have money set aside for your class to visit Frost for free. So that is an option available to you, and I'll talk more about how that will work. And I also wanted, we have some information about how it works and how you deal with food and, you know, parking and all of the stuff that you'll need to talk to your admins about, but that information is available. And then I wanted to briefly touch about, you know, our exhibitions. Obviously, we hope that you'll come to work with Mammoth, but we do have a 3-floor aquarium. We do have a planetarium, and we do have multiple exhibitions. Power of Science, which is one of our new exhibitions. It opened just before the pandemic, so many people who haven't been taking field trips haven't seen it yet. And it really deals with local scientists. We have the Feathers to the Stars, which is all about, it's everything from dinosaurs to airplanes. Anything that flies is going to be in this exhibition, including the paper airplane challenge, which the kids really like. And then we have our traveling exhibition. So currently it's Skin, Living Armor, Evolving Identity, but this summer, starting in May, we are going to be having a Sherlock Holmes exhibition. So it is a go and solve a crime, and your students will get to use different forensic techniques to actually kind of play their way through the exhibition. So yeah, it's a lot of fun. And then we have the Me Lab, which is really designed for 4th grade students. It was specifically a tie-in to the 4th grade science curriculum there, but it is something that, you know, a lot of middle school and high school students would appreciate as well. And then we have educator guides. So this is one of the things that we've noticed when people come visit us. They don't actually know about. We do want to make sure that your visit is really tied into your curriculum. So we do have educator guides that give examples of activities at every different grade level, from kindergarten through 8th grade. Some of our exhibitions have a high school tie-in, some of them do not. If you're interested in high school activities, you can always reach out and email me, and I would love to talk to you more about that. But we also have a Mammoth tie-in. So obviously we do have Mammoth activities, and I would like to walk you through one of them, kind of similar to how we did Chewing on Change. I'd love to kind of work with you as if you were a student. One of the things that we think about when we think about informal science education is it's not just giving your students the chance to maybe see stuff and participate in things that they wouldn't have been able to participate in outside of a science museum, but also give you as an educator a chance to do some different activities and kind of have a little bit of fun, hopefully, and help your students kind of think in a new way. So 2 of the things that we think are really crucial for developing young scientists are really from the nature of science perspective. One is getting comfortable using induction and inductive thinking as well as deductive thinking. And the other is getting comfortable with this idea that scientists don't always disagree, or sorry, scientists don't always agree, but that doesn't mean that one's right and one's wrong. So being able to deal with the fact that there might be different interpretations of the same evidence, but that they all are really still based in science evidence. And so these are two kind of higher level skills that we know that students can struggle with, especially once they get to college. So one of the priorities of our lesson plan design has been to make sure that we incorporate these skills. So I'm going to take you through the Mammoth guide. I'm going to stop my screen sharing for the time being. And I believe Stephanie shared so I went ahead and removed the K through 5 guide for you, but it is available. The whole thing is available on the website. And for 6th through 8th grade, to really try and build on these skills, we're doing something with extinction. So we know that mammoths, starting about 12,000 years ago, and ending maybe about 3,500 years ago on some very remote islands, ended up going extinct. We don't see them there today. So our curriculum is really designed to kind of help students build their understanding of extinction while also giving them the ability to kind of practice some of these new skills. So what we are going to do, I'm going to share my screen again, is we are going to go back in breakout groups. I hope the same breakout groups, but if not, it's fine. I'll make new friends. And I've given you some different animals. I've given you 12 animals. And they're all extinct animals. Now, unlike the mammoth that went extinct thousands of years ago, these animals are ones that went extinct in the past 100, 125 years. So you're going to look and try and group the animals. So your job is not to get the right answer. Your job is to figure out what are the rules for how you would like to divide the animals into groups. So do you want to divide them by time? Do you want to divide them by calls? How would you like to divide these animals that went extinct into groups? And then when we come back, you can chat a little bit about what rules you used or what rules kind of you think would work well. And we'll see if everybody came up with a similar answer.
For professional development, and you'll be able to go back and review that that recording there. Awesome. Any other questions?
Really quickly, what is our class size limit for the Frost Museum field trip if we're allowed to go?
Typically we say 30 students, but we have certainly we understand that this year teachers have larger class sizes for reasons outside of their control. So we can make minimal kind of accommodations if need be.
30 is fine. It's to prime the students to make sure that they're on their best behavior. So I only pick the best.
I see.
And what's that number again?
30.
30, okay.
Yes. Awesome. Okay. No other questions at the moment? We're doing good on time, y'all. So I think we're going to be able to end a little bit earlier for you. I just got a couple small things to just mention real quick. One is back to our shameless plug here. We just kind of did a final reflection. We are in the House and Senate with a bill, and this bill is to encourage the legislators to help fund and expand this program so that we can continue to grow. We've reached about 60% or 67% of the counties around the state. And as the name implies, we want to put scientists in every Florida school. And so that's a big ask and a big accomplishment to make. And Miami-Dade is a fine example of that. We've hit 25% of your schools so far. So we have a lot more to do. And it is just Brian and I right now. So I handle Miami pretty much by myself, other than events like this. I have to have him with me all the time on things like this. So we ask your support, and we hope that you would consider sharing your experiences if you do social media. I'm posting in the chat box right now, or I'm trying to, a list of the tags for the Miami legislators, if it'll let me. There it goes. And we would love it if you Twitter, tweet, Facebook, Insta, whatever it is you might do, if you would share out with legislators your experience with us and with the Frost, that'd be great. And you can also tag the University of Florida and of course the Thompson Earth Systems Institute, for which we are a part. And those handles are there as well. So you can learn a lot more about the program and even provide us feedback should you not do social media. There is a Google form in here that we would even love testimonials, because we share that with the legislators as well, and with district officials, letting your district officials know that this experience is worth your time. And we appreciate that time, knowing how busy, especially these days, you guys are. So we thank you for taking your time today to be with us. And I thank the Frost, our partner, Dr. Kate Carter, and of course, Dr. Bruce McFadden and Jeanette and Dr. Bokor. So everyone for being with us today and taking part of their Saturday to share these great resources. We hope that you enjoy sharing them with your students. And at this time, we'd like for you to just take a quick moment to fill out an exit survey for today's experience. That is the final thing I'm putting in the chat box there. If you'll take a moment to do that, and I think once you are done with that, you can go ahead and sign out, and we'll follow up with you with emails and packets in the mail. I'm going to stop sharing the screen too, so I can see everybody's faces.
I was noticing that there was like the sign-in sheet for the PD from Dade schools. Are we supposed to do anything to confirm that attendance, or how does that